Hello, this is a short summary of the Research Ed 2021 talk I gave on dealing with misconceptions, p-prims and the refining raw intuitions approach. And it's intended for people who either couldn't make the conference or who couldn't make the session. So I hope you enjoy. Okay, I'd like to begin with a historical analogy that I think neatly illustrates what I see as the potential of the p-prims approach towards looking at students' misconceptions. And it's to do with the discovery of the muon. Now, at this time, physicists were quite happy thinking of matter as being made up of three fundamental particles: the proton, the neutron, and the electron. So the discovery of a fundamental particle that was similar to the electron, but heavier, which was called the muon, was something of a surprise. And I loved Isidore Isaac Rabi's famous response to the discovery when he looked at it and asked, "Who ordered that?" Over the next few decades, the problem got worse rather than better. Hundreds of apparently fundamental particles were discovered, and they became labelled as the particle zoo. Enrico Fermi suggested that instead of being celebrated, physicists who discovered a new particle should in fact be severely punished. Happily, though, the problem was ironed out. The particles in the particle zoo weren't truly fundamental. Instead, they were made up of a small number of more fundamental particles. And this simplified the particle zoo and tamed the particle zoo. The Standard Model is, of course, the most successful scientific theory in the history of humankind. Probably the scientific theory, though, with the least inspiring name. The reason I mention this is if one does a search for misconceptions in physics, let's say, one discovers the shocking thing that more and more misconceptions are being discovered over time. And it can be quite intimidating trying to make sense of this, especially if you're planning a lesson or planning a scheme of work. How do you manage all the myriad misconceptions that students may hold, and how do you make sense of them? Well, it's my suggestion that this can be simplified, and the most promising candidate, in my opinion at least, for this simplification process is what's become known as the resources framework, put forward by the physics education research community. And examples of researchers who have written on this are Andrea De Sessa, David Hammer, and Edward Reddish. Reddish and Co. in 2015 summarized the resources framework by suggesting three lenses through which we can view how students construct meaning in physics. The first lens is embodied cognition. This is the most primitive level. It's our experience as living organisms. So it's the idea that what goes up must come down. It's built into our way of thinking that when it doesn't happen, quite often it can come as a surprise, even if theoretically we understand that things that go up don't always have to come down. It's a very basic way of thinking about the universe that De Sessa labels as a phenomenological primitive, or a p-prim for short. The second lens is encyclopedic knowledge, and this is the varied productive resources which are used in a dynamic way. So, for example, previous knowledge. So, children, if they've played with a helium balloon, recognize that it's the type of object that won't necessarily that even if it goes up, it won't necessarily come down. Other examples of encyclopedic knowledge are sources taken to be authoritative. That's statements by your teacher, possibly, or perhaps what you've understood by reading a textbook, or it could be also the results of calculations that you've performed using tried and trusted formulas such as the formula for speed and so on. The third lens is contextualization, and the activation of these resources depends on conceptual, epistemological and affective factors. Now, there's a lot of research on the conceptual and epistemological factors, but the affective or emotional factors often aren't the subject of quite so much research, and they are important, particularly when we're dealing with school-age students. And the example of this, I would say, is who are you going to trust, me or your lying eyes, as Groucho Marx famously said. Now, the main lens I want to focus on is the embodied cognition lens. And this is, I think, a very rich seam to mine in order to improve our teaching. And it relates, of course, to de Sesse's phenomenological primitives, or p-prims. And it is, I think, this level that often trips students up and makes them reluctant to accept the formal scientific knowledge we are trying to communicate to them. What is a p-prim? Well, p-prims, or phenomenological primitives, are simple abstractions from common experiences that are taken as relatively primitive in the sense that they generally need no explanation. They simply happen. Okay, let's look at what I think is a good example of a p-prim.
Okay, one last time. These are small, but the ones out there are far away. Small, far away. I forget it.
The difficulty that Father Dougal was having was he was applying a p-prim inappropriately. So he was using the p-prim that small objects look small and large objects look large. And so because they look the same size, he assumed they were the same size. P-prims are not misconceptions, but they can generate misconceptions when they are wrongly applied. A p-prim is like a semi-transparent filter. The world may look wrong when viewed through it, but only when we look out through the wrong p-prim. For p-prims, context is everything. Father Dougal is not seeing the world correctly because he's looking out through the wrong p-prim. Now, it's important to note that p-prims aren't always wrong. So when we apply the Father Dougal p-prim to this photo of Arnold Schwarzenegger and Danny DeVito, we can conclude correctly, using the p-prim, that Schwarzenegger is actually taller than DeVito. However, if we apply it to the wrong context, so the Earth looks much larger than the Sun from our perspective generally, but the Sun is still larger than the Earth in reality, so we're misapplying the p-prim if we apply it to the Earth and the Sun. De Sesse provides a list of p-prims. These include Ohm's p-prim, the idea that output decreases as resistance increases. This just doesn't apply to electrical circuits, it also applies to a wide range of contexts in the real world. So for example, if you're walking through mud, you expect to walk more slowly because the resistance has increased. Another one is the dying away p-prim. The idea that all effects spontaneously decrease in amplitude, and very often when this is applied by students, it's the idea that, for example, if you strike a tuning fork and it starts making a noise, students don't always appreciate that a mechanism is required to account for the decrease in amplitude. They just assume that all effects spontaneously decrease without any mechanism to account for the decrease. Another one is the idea of passive resistance, the idea that objects can passively resist or block motion without actually exerting a force. Now, one very valuable idea from the resources framework is put forward by David Hammer, when he suggests that perhaps in teaching we should think of refining rather than replacing raw intuitions. An example of this, let's look at Hammer's suggested approach in the context of a book or any other object when it's in equilibrium. Now, students have no problem accepting that gravity produces a force, the weight of a book, which makes it accelerate downwards. The problem is when the object is resting on an inanimate object such as a tabletop. They think of the tabletop not as exerting a force, but instead of just simply passively blocking the force of gravity, or alternatively stopping the book from moving, not by exerting a force, but rather by just getting in the way of the book. Now, to get students to accept the proper scientific understanding of this, one way of doing this is to show them the example of a spring on the table. So you then rest the book on the spring. Now, students have no problem accepting the idea that a spring exerts an upward force on the book, and of course that counters the downward force of the weight of the book, so the book is in equilibrium. Now, having gone through the example of a spring, students are much more likely to accept the standard account of equilibrium of an object resting on a tabletop. In other words, that the weight of the book is tending to make it accelerate downwards, but the weight is countered by the table pushing upwards on the book, shown by the blue arrow on the diagram. And students are much more likely to accept this once you have introduced the spring example. So I think it's a really good example of the idea of refining raw intuitions rather than trying to replace them. Another example where taking account of p-prims is very useful in teaching is, I think, in thermal physics, when we introduce it in Key Stage 3 and Key Stage 4. So, for example, when we give students a list of good conductors and explain that a good conductor is a poor insulator and a good insulator is a poor conductor, in effect what we're doing is we're activating the Ohm's p-prim in terms of thermal physics. So students now have the unconscious expectation that something can't be good at one thing and also good at its opposite. Now, this stores up a problem, particularly if next lesson we say we introduce the idea of emitting infrared radiation or absorbing infrared radiation. And it's very confusing to students having because we've activated the Ohm's p-prim in terms of thermal physics, to accept that a matte black surface can be both a good emitter of infrared radiation and a good absorber. Nelms in 2004 had an intriguing suggestion using the p-prim approach, and she suggests that before we cover this idea of absorption and emission of infrared radiation, we try and activate an alternative p-prim for our students. And the p-prim we're seeking to activate is the Matthew effect p-prim. And this essentially comes from the Gospel according to Matthew, where there's a famous verse which says, "To him that hath, more shall be given." So, activating the Matthew effect p-prim, using an example such as a good communicator is good at listening and good at speaking, makes students more likely to accept the idea that something can be a good emitter and a good absorber. Misconceptions research in education has been hugely valuable. For many teachers, including myself, it is the educational research that has the most immediate and tangible practical benefit in terms of teaching. And it's what made me interested in educational research, because understanding misconceptions, I think, helps you teach better. It also emphasizes that students' prior knowledge is important, and if we ignore the contribution that prior knowledge can make to understanding, either in blocking it or in helping students to acquire new knowledge, I think we're doing a disservice to our students. The downside of misconceptions research, as it is sometimes applied, is that it emphasizes the negative impact of students' prior knowledge. In other words, we're seeking to eliminate the nasty, messy, everyday thinking, and we want to root that out and replace it by the proper, bright and new, shiny, scientific thinking. And I think that's not the best approach. I think p-prims and the resources framework offer a promising alternative, a sympathetic awareness of student thinking that I think could improve teaching and learning in science. Now, in closing, what I would suggest is perhaps using p-prims, what we can do is we can develop a standard model theory of students' misconceptions that will help teaching and learning. In other words, we won't have to worry about hundreds of individual misconceptions. We can classify them into very broad classes of misconception and provide teaching which helps students learn better, because we're taking due account of the effect of p-prims on their thinking. And I'd just like to finish by saying that although these ideas aren't mentioned explicitly in the recent book that I co-authored with Adam Boxer and Hina Dave, they certainly informed the approaches that I used in the physics section. Now, if you want to get a discounted copy of the book, just follow the instructions on the screen. And finally, here's a list of the references I used in compiling this talk. I will put a full list of these references on my blog with links to the papers if I can find them. If you're new to the p-prims and the resources framework, I'd particularly recommend starting with Reddish & Quo 2015, which I think is an excellent introduction to this topic. Thank you.